In lesson 2.1, we learned that reflections are the problem. What we're going to learn in this lesson is that the way to control reflections is with transmission lines. Remember, we established a rule in lesson 2.1 that if we send a signal down a conductor, it reflects off the far end of the conductor back toward the source. And there was only one exception to that rule, and that was a very specific case. Well, the specific case is a transmission line, and more than that, it is a transmission line that is terminated in a very special way. That is what we are going to cover in this lesson. Now, in theory, a transmission line looks like an infinite series of L's and C's. Here we have a copper trace. Here we have typically the return path on the plane. We look at the trace as though it consists of a large number of L's and C's, the inductance of the trace and the capacitive coupling between the trace and the plane. Now, in practice and in reality, this is a distributed inductance. It's distributed all the way along the trace. And this capacitance is a distributed capacitance all the way along the trace, between the trace and the plane. We don't know how to draw distributed inductance, and we don't know how to draw distributed capacitance. So what we are drawing is what we call the lumped equivalent. Here's a lump of inductance, here's a lump of capacitance, and here's another lump of inductance and another lump of capacitance, and so on. So this is a lumped equivalent of what is actually a distributed amount of inductance and a distributed amount of capacitance. And we give values to these L's and to these C's, and we call it, respectively, the intrinsic inductance of the line and the intrinsic capacitance of the line. If we look into this line, it has an impedance. I mean, this is an LC circuit. So an LC circuit has an impedance. And it works out that the impedance looking into that line is given by this expression. It's the square root of L over C, where L and C are the intrinsic inductance and intrinsic capacitance. Now recall that L has a voltage phase shift of plus 90 degrees. We're dividing it by something that has a voltage phase shift of minus 90 degrees. The result is zero phase shift. Anything with a zero phase shift is resistive. And so what this characteristic impedance is actually resistive. It looks like a resistor. So remember this, we're looking at this as an ideal transmission line. There's no other resistance involved in here. These are ideal components. And in the case of an ideal transmission line, the impedance looking into it is that of a pure resistor. Now, if we shorten a transmission line and then terminate it in an impedance that is equal to Z0, let the terminating resistor, RL, equal Z0. Well, the line still appears infinite in length, and the input impedance will still be Z0, and there will still be no reflections or echoes coming from the far end of the line. If a finite length of transmission line is terminated in any other value, or if there is a discontinuity somewhere along the internal impedance, then there will be a signal reflection at that point. So we've got this line down here. If we terminate it in RL equals Z0, it still looks like an infinite line. There will be no reflections back. If we terminate it in something other than Z0, then there will be reflections back. If we do something different in this line, if we damage the line in some way or other, suppose for a minute we change this capacitor value and that inductance value. Now that doesn't make a lot of sense because this is a distributed inductance and a distributed capacitance. But hypothetically, let's just say we changed these two values. That would provide a change in the impedance at this point. We would call that an impedance discontinuity, and then there would be a reflection off that point. Now, proper terminations absorb all the reflections. Remember this transmission line simulator from the previous lesson. I'm going to show you this again about what we mean by absorbing reflections. So here is our simulator. Remember, this is distance along this axis. This is a trace. This is the signal at the near end of the trace. This line is time. We're looking at the signal right at this point. This line is also time. We're looking at the signal at the far end of the trace, or right down here. Now I've got a trace with a characteristic impedance of 50 ohms. I'm going to terminate it in 50 ohms. I'm going to send a single pulse down the trace, and we'll see what happens. And what happens is nothing. There's no reflection. There's no nothing. I'm going to send a square wave down this line, and I'm going to let it free run, and what I get is something that is absolutely perfect, just exactly what we want it to be. But if I terminate it in something other than the characteristic impedance, let's say I terminate it in 10 ohms and send a square wave down the line, well, then I do get a bunch of reflections. And if I terminate it in something other than the characteristic impedance the other way, let's say 250 ohms, well, I will get a bunch of reflections again, going up and down the line. So proper terminations can absorb the reflections. Improper terminations will not. Now, how do we know what's going to happen at the far end of the line? And the answer to that is wrapped up in this thing we call the reflection coefficient. The reflection coefficient, rho, determines the sign and magnitude of the reflection. Rho is given by this formula, RL minus Z0 divided by RL plus Z0, where RL is the load at the far end of the line, and Z0, of course, is the characteristic impedance. This is a handy formula to remember. I will have to admit I have trouble remembering it because it's kind of hard to remember whether the resistor comes before or after Z0 and whether the minus sign is on the top or the bottom. But nevertheless, it's a good formula to try and remember so that we can understand what's happening in our transmission lines. And this reflection coefficient can have a range of values that range from -1 to +1. Let's say we have a very high resistor or open circuit at the far end of the line. Well, then this formula becomes RL divided by RL, which is 1. We get 100% reflection, and it is positive in sign. And we saw that in a couple of the illustrations. Let's say we short circuit the line, let RL be 0. Well, then we have minus Z0 over plus Z0, or we have -1. So if we have a short circuit at the end of the line, we still have 100% reflection, but it's minus in sign. It's opposite in sign to the driven signal. Let's let RL equal Z0. If we do that, then this numerator goes to 0, rho is 0, and there is no reflection. So the reflection coefficient is what tells us the sign and the magnitude of what the reflection is going to be. Now, sometimes we can wonder, is there a contradiction between a variety of the rules that we're talking about? First, current flows in a closed loop. Current must flow in a loop. Current is constant everywhere in that loop. Yet, there's a finite propagation time for the signal to propagate down the trace. And reflections can't happen until the signal propagates down to the end of the trace and finds out how the trace is terminated. The signal doesn't know if it's going to reflect back until it gets down to the end of the trace and sees what's there. So, is there a contradiction wrapped up into all of these things? And of course, the answer to that is no. And I'm going to show you a couple of animations to show you how this works. Here is an animation of how a signal propagates down a transmission line that is properly terminated. The signal starts down the line, and there's the loop. Let me show you that one more time. The signal propagates down the line, loops back. Down the line, loops back. Then if it's a square wave, well, then it just has this loop that circulates around the line. Remember, this is an ideal line. It's a lossless line. There's no resistance in the line. And so we have a closed loop. The signal flows in a closed loop. The signal is constant everywhere in the loop. The signal propagates down to the end of the line until it hits the termination. Now, if we look into this line, there is a certain impedance. Well, that impedance, along with the voltage driving this line, tells us what the current's going to be. So we know what the relationship is between the voltage and the current going down this line by Ohm's law. So if there's a certain amount of voltage and current going down this line, there's a certain amount of energy in this line. If this line is properly terminated in a terminating resistor, all of the energy that is propagating down the line gets terminated in that terminating resistor and dissipated as heat. There is no energy left to go anywhere else. And specifically, there's no energy left to reflect back up the trace. That's kind of how the mathematics works in transmission line theory. Now, contrast that with what happens if we have an open circuit. We have the same signal coming down here, but at the end, we kind of hit this capacitor. There's no place else to go. We overcharge that capacitor and then send the energy right back up the line again. So the signal propagates down the line, hits the end of the line, builds up and forces its way back again. It's 100% reflection with an open circuit like this, and it's positive in sign. If we have a shorted signal, shorted line, then the signal comes down here and wraps around the end of the line, starts charging up the capacitors on the opposite side, and goes back up the line again. So the energy comes down the line, wraps around the short circuit, back up the other way. We get 100% reflection, and it is opposite in sign. So no, there are no contradictions in the various rules that we are talking about. And these are three illustrations of how a signal propagates down a transmission line. So now the solution to the reflection problem on printed circuit boards has these two parts. First, we design our traces to look like transmission lines, and then we terminate them properly in a termination where R is equal to Z0, where Z0 equals the square root of L0 over C0. So, first question, how do we design transmission lines on a circuit board? Well, we need to control the relationship between trace width, trace height over the underlying plane, and the dielectric material. Those are the three big factors, and to a lesser extent, trace thickness. So, controlled impedance of a transmission line on a printed circuit board means controlled geometry. There are many web-based resources for impedance calculations, and all of them, I believe, are based on formulas like those I'm going to show you on the next slide. These are old formulas. They were formulas that were developed back around the 1990s. They were okay then, but they are not very accurate, and generally they're not accurate enough for today, and they're especially not accurate enough for differential impedance calculations for differential traces. Now, we used to have formulas like this. For an asymmetric strip line that looked kind of like this, this is what the formula we used to use was. That is what we can call an ugly formula. It was only good to about 5 or 10% anyway, and even though I like numbers and I like working with formulas, I have to tell you that I could try and solve for the impedance of a trace 3 different times and I'd still come up with 2 different numbers. These are really difficult formulas to work with. So how do we do it today? Well, we have to use design tools. and tools that are based on field solvers. So if you have a high-end PCB design tool, that's what you want to use. We can use simulators, and there are a few special case calculators that can be used. This is an illustration of the Mentor Graphics Expedition tool. That's what we used at UltraCAD, and it will give you trace impedances and differential impedances. This is the Hyperlinks simulator, and this is the Edit Coupling Region tab and menu item on that simulator. And here it will tell you what the trace impedance and the differential impedance is. Here is a Polar Instruments calculator. It's their Quicksolver version. And if you look at this click on this little box down here, it gives you differential impedance and single-ended impedance and all kinds of information about trace configurations. I like this calculator very much for board designers, and I am high on this calculator. And then UltraCAD has a differential impedance calculator that we offer that we think compares favorably to the Polar calculator, although it is much less flexible than the Polar calculator is. But on the other hand, it's a lot less expensive too. Now, remember from lesson 1.4 that trace geometries can be scaled. So we had this figure that showed what the electromagnetic field was around a pair of traces, 8 mil traces, 8 mil separation, 5 mils above the plane, and ½ ounce thickness. And then we just scaled everything up by a factor of 2, 16 mil traces, 16 mil separation, and so on. And the electromagnetic field distribution looked the same, and the impedance looked the same. So one more emphasis that it is the distribution of the electromagnetic field that determines the impedance, more so than the specific dimensions of the trace. And when we sit there and say the way we control the impedance is through a controlled geometry, well, we are trying to control the geometry that determines what the electromagnetic field distribution is going to look like. Okay, so now that we have designed the traces, how do we terminate them? And I'd like to refer you to a particularly good reference on this topic, Termination Techniques for High-Speed Buses, by these two people way back in 1998, but it's still an excellent article. And last I looked, this article was available on the EDN archive page. You could still call this up. And what I want to suggest is it's the engineer's role to select the termination technique. It's not the board designer's role. This is an engineering problem that needs to be solved. But it's the board designer's role to know if any technique has been used at all and to ask the question, if not. Now, there are several common termination techniques that are used. They go by the names parallel, AC, series, and then Thevenin and diode. The first three of these are pretty common on circuit boards. The last two really aren't very common. The parallel termination simply involves putting a resistor at the far end of the trace, a resistor whose value is equal to Z0. The pros, we terminate to either ground or to VCC. The value is very easy to determine. There's only one additional component, and it performs very well if there are distributed loads along the line. But there are a couple of problems, and the most significant one is that power is dissipated in this load resistor all the time. And if you have lots and lots of traces that need to be terminated, well, then that might amount to quite a bit of power. Power requirements are simply too high for some logic families, and it may have negative implications for signal levels and noise margins in some cases. So this is a good, easy termination technique, but it does have some practical limitations. Now, some of those limitations are overcome when we put a capacitor in series with the load resistor. This blocks the DC flow, but still terminates the transmission line correctly for AC signals. But this has some problems. The value of C is kind of difficult to optimize. It's easy to get it to be too large or too small. It does require two components instead of one. And it can lead to some significant timing problems if we have long identical bit strings. This really works well for a clock pulse where you have a 50% duty cycle. But if you have, say, a 100% duty cycle for a little while, then this capacitor can charge up, and that can result in some unfortunate side effects. This is an illustration of what we call series termination. We put a resistor at the beginning of the trace instead of the end of the trace. And the value of this terminating resistor right here is such that this resistor plus the output impedance of the driver together equals Z0. Now, the pros, this is one component, and it's the smallest cost in increased power. There's no DC load at all. But there are a couple of problems with this, too. It can be difficult to optimize this series resistor. The output impedance might be different for a logical 0 than it is for a logical 1, and therefore you can't optimize this resistor for both states. And so you have to compromise on, say, a middle ground or favor one state over the other. And then there is one reflection that comes back before the signal is absorbed in the terminating resistor. This termination technique came into favor with the PCI bus on the personal computer back around the 1990s. Then the other two termination techniques are the Thevenin termination and diode termination. And to be honest, in my career in board design, I've never seen these techniques used. So we're simply going to brush by them in this lesson. Now we can ask the question, what should Z0 be? If I'm designing traces, what should Z0 be? And there are some people who have some definite opinions about that. There are some engineers who will allege that 50 ohms is optimum, and they allege that they can prove that some way or other through mathematics. I'm not sure I believe that. Typically the range is about 30 ohms to 80 ohms. Too high can aggravate some noise problems. Too low can cause power problems and current drain problems. And so, as far as I'm concerned, it can be whatever you want it to be within kind of this range. The only really significant rule is that whatever it is, it has to be constant everywhere along the trace. Now we can get to this question of the absolute value versus a relative value of Z0. And I will argue the absolute value of Z0 is not important. You can pick whatever value you want. The absolute value is not important unless you're going to mate with the outside world, in which case you now have to match what happens at the mating point between your design and the outside world. You're mating with mother and daughter boards, and there are some special component requirements where the component requires a specific impedance. When I say mating with the outside world, UltraCAD designed a lot of boards for the video processing industry. And so we always had a lot of connectors on our boards that were 75 ohm connectors. Every trace that attached to a 75 ohm connector, of course, had to be a 75 ohm trace. But after that, when you got to the other side of the integrated circuit, well, they didn't have to be 75 ohm traces. And interestingly enough, some of our customers understood that and some didn't. Some of our customers said, this is video, all traces have to be 75 ohms, period. And other customers understood that, yeah, the traces that connect to the connectors have to be 75 ohm traces, but, you know, UltraCAD, you're free to design the rest of the traces the way you want to. But again, the guiding rule is that Z0 must be constant along the trace, and especially as a trace moves from one layer to another. So whatever Z0 is, it has to be constant. And then the terminations have to match Z0, whatever it is. Now, this is one reason for specifying an absolute value, such as 50 ohms. But I want to emphasize that that is a policy reason for specifying an absolute value. It is not a technology reason. The policy reason might be, I only want to have one value resistor that I'm going to stock in my inventory, and so all the terminations are going to match that value resistor. That's a policy determination, and that's fine. There's nothing wrong with that. But recognize that that is a policy decision. That is not a technological decision. Whatever we pick, board fabricators can typically hit about plus or minus 3%, 3% to 5%. And the reasons for that and the reasons for the impedance variations at the board fabrication shop are temperature gradients during fab, pressure gradients, non-uniform thicknesses, material non-linearities, and so on. The board fabricators have a lot of problems at their end that they have to deal with. And so no matter how close we want to specify things at the board design standpoint, the fabricators still are kind of stuck in this range unless you want to pay a lot of extra money to try and get tighter. On the other hand, there's not normally a lot of reason to get much tighter than that. Plus or minus 3% is usually good enough. And then when we talk about really fast circuits, control over the geometry can be tricky. Remember when I said the way you control the impedance is to control the geometry. And you control the geometry by trace width, trace height above the plane, and the dielectric. Well, here, if we have a dielectric that's got a fiber weave that looks something like this, well, this trace is now in a different environment than this trace is. So does that mean we're going to start having some impedance discontinuities along here? Well, if we're dealing with relatively low rise times, relatively slow circuits, the answer is no, this is going to be fine. If we're dealing with really fast circuits, well then this might begin posing a problem. And the idea of critical length begins to come in an analysis like this. Now, if you're concerned about that, there are some high-speed materials that you can buy that have a much tighter weave and so on. But in this lesson, I simply want to point out that control over the materials is not necessarily an easy thing to achieve. So here are the takeaways from lesson 2.2. The solution to the reflection problem has two parts. Design our traces to look like transmission lines. Those are called controlled impedance traces, and we control the impedance of those traces by controlling the geometry. And then we terminate those lines in their characteristic impedance. The reflection coefficient gives us the sign and magnitude of the reflection if the line is not terminated properly.